The concept of using light as a weapon has intrigued weapon designers for centuries. The first such system hypothesized was the Archimedes heat ray. According to legend, he had used a series of mirrors to focus sunlight on ships of the Roman fleet as they invaded Syracuse, setting them on fire. During World War II, various stories of engine stopping rays had been reported, including Nazi supported studies into a directed X ray beam weapon. Researched by the German electrical engineering company Siemens Schuckert, the concept hoped to disable piston engines by ionizing their combustion chambers through a directed bombardment of X rays. Fast forward 2 decades, and it would not be until 1960 for the light weapon to reach the realm of feasibility, when Theodore H. Maiman operated the first functioning laser at Hughes Research Laboratories in Malibu, California. In civilian applications, lasers would soon grow in power. With the ability to focus kilowatts of energy onto a small point, their use in industrial welding and cutting expanded rapidly, though their initial military use has been more indirect, being used primarily for range finding, targeting, and ordnance guidance. The first use of lasers to damage targets directly were laser blinding weapons. These were first used during the Falklands conflict and the 1980s war between Iran and Iraq. Because relatively low energy levels could permanently blind combatants, their use led to the Protocol on Laser Blinding Weapons in 1995. These protocols would eventually be adopted by 108 nations by 2018. Lower powered systems intended to temporarily blind or disorient its target, called dazzlers, are still in use today by both the military and law enforcement. Laser systems that directly use highly focused light as a ranged weapon to damage a target are part of a class of arms known as directed energy weapons, or DEW. Despite huge funding into research efforts, both by the US government and several other nations, to date, no known laser directed energy weapon has ever been used against military hardware on the battlefield. Shortly after Maiman's discovery, aggressive research immediately led to the gas dynamic CO2 laser in 1968, which accomplished continuous power levels of over 130 kilowatts. By 1980, megawatt beams were achieved by the mid-infrared advanced chemical laser, or MIRACLE, making it the most powerful continuous wave laser in the United States at the time. Its original goal was to be able to track and destroy anti-ship cruise missiles, though mixed results from testing did not lead to any functional weapon system. Creating a functional laser-directed energy weapon system is far more challenging than simply building a high-power laser. Such a system not only requires a powerful laser source, but also the necessary optics to focus the beam at the desired distance, a method for target detection and tracking, a mechanism for accurately and rapidly steering the beam onto the tracked target, and finally a real-time computer system capable of control and coordination of the weapon's systems. One of the most significant limitations of a laser-directed energy weapon is its restrictive targeting characteristics. By their very nature, they can only engage targets by line of sight. Atmospheric effects can also negatively affect their use, both for target tracking and beam propagation. Absorption, scattering, and turbulence have to be taken into account. Adverse conditions such as rain, fog, and smoke can outright make it impossible to even employ the laser at all. But even in ideal atmospheric conditions, as a laser beam's power is ramped up, a critical intensity is reached and nonlinear effects set in. The laser itself influences the atmosphere, starting with simple heating through absorption and culminating into atmospheric ionization. While the amount of energy absorbed by the atmosphere is dependent on the wavelength of the laser, this plasma breakdown starts to occur at energy densities of around 1 megajoule per cubic centimeter. Known as thermal blooming, it causes the laser to defocus and disperse energy into the surrounding air. This phenomenon inherently imposes a limit on the maximum intensity which can be transported through a given path in the atmosphere. Laser systems that operate on short, high-intensity pulses are particularly sensitive to these effects. Beyond the complications of the atmosphere, Simply transmitting enough energy to the target is a challenge in itself. With conventional munitions, all of their kinetic or chemical energy is released with no noticeable time delay upon impact. A laser beam, however, needs some time to heat up the exposed target area until significant damage occurs. The tracking mechanism of the laser system has to be able to maintain a consistent track of the target while constantly steering the beam during this duration. Even when a beam is able to successfully track a target through the atmosphere and transmit enough energy to it, laser weapons must contend with the reflectiveness of the target's coatings. Depending on the wavelength of the laser radiation, defensive coatings can reflect up to 95% of the radiation away. Fast and erratic moving targets can also force the beam to spread, preventing any significant damage. Furthermore, laser directed energy weapon systems tend to be large and consist of fragile optical instruments that are vulnerable to contaminants and misalignments. Modern laser directed energy weapon systems research can be put into two categories: industry funded projects that use civilian off the shelf industrial lasers, and government funded research that tend to focus on high power laser systems. These strategic defense specific systems produce continuous power levels exceeding civilian lasers by one or two orders of magnitude. Industrial lasers are primarily found in lower powered tactical systems. Both Boeing and Raytheon have spearheaded research into such tactical laser weapon systems using industrial solid state lasers. One of Boeing's technology demonstrators consists of a modified Avenger air defense vehicle with a laser directed energy weapon in place of its missile launcher. As a laser source, the system uses a commercial 2 kilowatt solid state laser and has demonstrated its effectiveness against unmanned aerial vehicles as well as explosive devices on the ground. Another more powerful tactical development by Boeing is the relocatable high energy laser system, or REALS. This technology demonstrator system combines four industrial manufacturing thin disk lasers into a 10 kilowatt system. Reels consists of the lasers as well as components for cooling, power supply, and tracking, all installed in a 40-foot relocatable shipping container. For Raytheon, one of their principal ongoing developments is its Laser Area Defense System, or LADS. The LADS weapons demonstrator is based on a modified phalanx air defense system that uses radar-controlled multi-barreled cannons. The phalanx system is installed on some U.S. Navy ships in order to protect them against close-in missile targets. Raytheon has replaced the cannon with an industrial fiber laser, successfully testing the concept against a variety of targets, including incoming mortar rounds. Both thin disk lasers and fiber lasers are two common approaches used in the manufacturing industry to scale solid state lasers to higher power levels. Because of the inefficiency of the conversion process, a significant part of the energy used to create the beam is lost as excess heat. This heat has to be transported out of the solid state medium in order to avoid overheating and destroying the laser. Additionally, the non-uniform temperature distribution within the amplifier causes a higher than ideal beam divergence of the resulting laser beam, reducing the delivery energy per target area. In order to combat heating, the light amplifying medium is cooled in a way that results in a consistent temperature profile, relying on its surface area design to achieve proper cooling. Both thin disk lasers and fiber optic lasers achieve this by their medium geometry. Fiber lasers, in particular, are ideal for weapon use due to the ends of the fiber itself being used to form the laser resonator. This allows a ruggedized design as no mirror alignment is necessary. Currently, fiber lasers deliver the highest continuous output powers of all commercial lasers, achieving up to 50 kilowatts. On the US government funded end of the spectrum, several programs have yielded solid state lasers that have so far reached power levels greater than their industrial counterparts. One notable example has been Northrop Grumman's Joint High Power Solid State Laser Program, which has produced beams in the range of 100 kilowatts. Despite these advances, the need to cool solid state lasers places a limit on their maximum power, restricting them to relatively short ranged tactical use. For a laser directed energy weapon system to be feasible for strategic applications, beam power in the megawatt range becomes a requirement. Power levels at this magnitude are predominantly achieved by chemical lasers, a focal technology of all strategic military laser programs. Chemical lasers work by using a chemical reaction to create the beam. The involved reactants are fed continuously into the reaction chamber, forming a gas stream, which functions as the light amplifying medium for the laser. Because the gas stream is continuously being produced while spent reactants are vented out of the laser, excess heat does not accumulate and the output power is not limited by the need for cooling. The Advanced Tactical Laser, or ATL, and the Airborne Laser, or ABL, has been the two most notable chemical laser directed energy weapons programs in recent years. What makes both of these programs so unique is that they are the first aircraft based laser directed energy weapons. The ATL is a technology demonstrator built to evaluate the capabilities of a laser directed energy weapon for ultra precise attacks against communications platforms and vehicles. Powered by a chemical oxygen iodine laser, or coil, it's speculated that its beam is capable of up to 300 kilowatts. The ATL system is designed around a standard C 130 cargo aircraft and can engage targets at a range of 10 to 20 kilometers. Its potential uses include covert operations, as well as situations in which civilian assets are mixed in with military targets. On June 18, 2009, it was announced that the ATL was successfully fired in flight for the first time. Over the next few months of testing, it proved successful in defeating ground targets, proving the concept. Of all the laser directed energy weapon programs explored, the ABL system is arguably the most prominent and recognizable. Built around a Boeing 747 designated as YAL 1, ABL is also powered by a chemical oxygen iodine laser, though one large enough to produce a continuous output power well into the megawatt range. ABL's primary objective is that of strategic missile defense. It's designed to target and destroy ballistic missiles while they're in boost phase, shooting them down from a range of several hundreds of kilometers. ABL's mission profile requires that it remains on station near possible missile launch sites for long durations. At the moment a missile launch is detected, the ABL would then immediately track and attack it. In addition to the incredible power of its main laser, the ABL also features an adaptive optic system, which is capable of correcting the degrading influence of atmospheric turbulence on the laser beam. This system is critical for the beam to reach its intended range. On March 15, 2007, the YAL 1 successfully fired its laser in flight, hitting its target, a modified NC 135E Big Crow test aircraft. By February 11, 2010, now fitted with a more powerful laser, in a test off the Central California coast, the system successfully destroyed a liquid fuel boosting ballistic missile. This test was the first time that a directed energy system destroyed a ballistic missile in any phase of flight. Several other tests with varying degrees of success were carried out in the days following. Despite these successes, in December 2011, it was reported that the project was to be ended after 16 years of development and a cost of over $5 billion due to concerns of the affordability and practicality of the system. However, research gathered from the program had spurred interest in future programs that focused on deploying lasers on unmanned combat aerial vehicles that could fly above the altitude limits of a conventional jetliner for the purposes of missile defense. Despite billions of dollars of funding and decades of research, laser directed energy weapons still remain primarily an experimental technology. However, smaller systems designed for short range, smaller threats such as UAVs, small aircraft and boats, inbound missiles, rockets, and mortars are starting to be fielded. Laser defense systems such as the US Navy's XN-1 Laws deployed on the USS Ponce and the Israeli Iron Beam air defense system are being used experimentally for low-end asymmetric threats. Though these systems are modest compared to the promises of the multi-billion-dollar programs of years past, costing less than $1 per shot, the versatility of these smaller, less expensive, laser-directed energy weapons may prove to be the future of the technology.
sharks with frickin' laser beams attached to their heads.